Hello, everyone, and welcome to this webinar about data visualization with Wolfram Language. Today, we'll be talking about different ways of visualizing data. We'll start with simple bar charts, histograms, pie charts, and so on. We'll move on to some more complicated things. As you can see from my screen, we have 6 notebooks for this webinar. Since the webinar today will be between 1 hour or hour and a half, we're not going to have time to go through all of them. These materials are taken from a WolframU course that you can take online, which I think takes about 2.5 hours or 3.5 hours. So this material is intended for a much longer session. Since we only have about an hour, I'm going to skip over some things. But just to give you an idea of what we'll be discussing, we'll start with the first notebook. We'll go through it because it introduces the most common visualization options, and I'm going to show you how to use them in Mathematica, and I'm going to show you what data types they are appropriate for. Then notebooks 2, 3, and 4, there are some very useful things, but I'm going to gloss over probably the majority of those notebooks. So I'll try to focus only on the things um, that I think would be useful for you. 5, I'll come back to it if we have time. It's about dynamic interactivity with your visualizations, things like tooltips and so on. It's I would say the least interesting out of all 6 notebooks. So that's why I'll leave it for last if we have time, and we probably won't. Notebook 6 is the final notebook, and I'll try to go through at least a good portion of that because that's where things get really interesting. So we'll start with just some out of the box visualization options, if you want to put it that way. Things that you can just plug your data into and then you get a nice visualization out of it. But in Notebook 6, we're going to be using graphical primitives to construct our own visualizations. So instead of having a ready to go visualization option, we'll start constructing it ourselves by combining different elements together. For example, axes and bars and menus and things like that. So I think that's where things get a bit interesting. Um, so yeah, that's more or less the plan for today's session. There is nothing highly technical or very complicated. So just sit back and relax. So, just a few words about the learning objectives. So, what is the point of doing visualizations? Um, Obviously, visualizations have a presentation purpose. So, if you want to share your results, your data, your insights with other people, having nice visualizations goes a long way. But it also can help you understand your own data better. Um, Sometimes seeing data in a spreadsheet can be informative. You can eyeball, you can kind of get some feeling for what's going on in the data. But sometimes a good visualization can give you kind of additional information that you wouldn't have seen just in the pure numbers. So, very general point about why visualizations are useful. And then the other learning objective that we are going to focus on is choosing the right data visualization function. So data typically is just numbers. It could be other things. We'll see. We'll be dealing with entities quite a lot, but fundamentally, data is just numbers. So you can visualize a piece of data in many different ways, and some of them are going to be useful, and some of them are not going to be useful. So we'll be focusing on which visualization is right for which type of data. Again, very general, kind of basic point. So we are going to cover scatter plots, charts, histograms, time series visualizations, tables, geographic, geocomputation, and actually many, many more. So let's get into it. So for this webinar, we are going to be using a dataset that comes from the Wolfram Data Repository. So the Wolfram Data Repository is one of the many repositories we have where people can contribute. They can upload their own resources, in this case, data. And then once the data is uploaded to the repository, anyone um, anyone can use it. Anyone with a mathematical license can use it from within their notebook. And the nice thing about the data repository is that data is sourced, so there is always a source. If you go to the oh, this is just a screenshot, but if you go to the bottom of of whichever data set you're looking at, you will typically find a source telling you where the information is coming from. And the other nice thing is that the data is cleaned up and normalized, and it's ready to be used in the best way possible in Wolfram language. So, for example, you can obviously you can find a lot of data on the internet, but sometimes you find, let's say, a CSV file that contains some cool data, but the dates, let's say that there are dates in the data, and the dates are strings, so you need to convert them to data objects to be able to do really cool things with them. Whereas with data in the Wolfram Data Repository, all of that is done for you beforehand. So um, it's um, it's very useful, especially for teaching and for demonstrating Wolfram language functionality, because you don't need to worry about the data cleaning part. Um, the data is ready for you to use, basically. And there are many different data sets. The one we'll be using is called US baby names by state, which will have the frequency of baby names in the US listed by year and state since 1910. So it's quite a big data set. And if you have downloaded the materials, by the way, from Big Mark or YouTube, you already have them. You already have the data set. If you're just working in your own notebook, this is how to get the data set. Let me uncomment this. This is how to get this specific data set that we'll be working with. And as you can see, very easy to import that data into your notebook. If you find another data set that looks cool to you, just replace the name of US baby names with your preferred data set from the data repository, and you'll be able to work with that immediately. But we already have that downloaded, and since I mentioned it's quite a big data set, I'm not going to download it now. So let's have a quick look at a slice of that data set to see. It's always a good practice to kind of have a quick glance at what you are dealing with before you actually start trying to slice it or parse it and so on. So um, a lot of data sets from the data repository come in a data set format, which is a nice way to visualize tabular data. It's your common kind of spreadsheet format type of visualization. You have the columns representing the different variables, and you have the rows representing each entry or each observation of those variables. So the specific data set we're dealing with here has different states. It has genders, has years, name, which is what we're mainly interested in, and it has a count of how many number of people with that name were born in that state for that year. So, for example, there were 349 people named Charles in Arkansas, United States, in the year 1918. So, we will be doing a lot of things with this data set. We'll be taking different elements out of it and visualizing them. We'll be slicing it all sorts of different ways. Since this is not really a webinar about data science specifically, or cleaning up data, or slicing data, most of those things will be done in initialization cells. So if I go to the bottom of this notebook, you will see, oh, sorry, I'm trying to, okay. So if we go to the bottom of the first notebook, you'll see that there's a lot of things already done for us. We have some helper functions, we have some importing and exporting of data, and we have, most importantly, we have all the slicing done for us. So, for example, here we have all the unisex name counts, so all the names that have been given to both males and females, and so on. So all of the different slices that we'll be dealing with come from the initialization cells. Just in case you're wondering, because sometimes we'll be looking at a specific slice, and you might be wondering, oh, where did that come from? It's all in the initialization cells. So as I mentioned, not really, we're not really talking about data cleaning here, but if you are interested, if you are curious how that is done, feel free to kind of inspect the initialization cells. So we can start by just taking a random sample of our data, and as I mentioned, I already kind of described what the data is showing us. But let's go through it again. There were 142 people named Carlos born in Illinois in 1968, for example. So I mentioned that data from the data repository comes in the form of a data set. And a data set is its own kind of data type, although not in the very strict programming sense, I don't think, in Wolfram language, but it has a head of data set. But a data set is just a wrapper for nested structures like lists and associations. So you can pass any properly formatted list or association or lists of associations and so on to dataset, and you get this kind of nice tabular view of your data. But under the hood, so to speak, the data remains in its list and association state. So if you want to revert back to that, you can always apply the function normal to it, which normalizes the data. So as we see here, we took a random sample of 4 entries from the dataset, and this is a dataset. If we want to revert back to a list of associations, we just pass that random sample to normal, and we get back our underlying list of associations. So both of these things, both the data set you see here and the list of associations, represent the same data, just in different ways. And we'll also talk about tabular a bit later in the webinar, which is yet another way to represent tabular data, but we'll get there in a little bit. So one of the nice things of keeping your data in a list is that you can pass it to the grid function, which creates this nice, much more simple than the dataset visualization type, but it still gives you this kind of minimalistic table view, and that again is very useful for just um, uh, quickly scanning what your data looks like in a more human readable format. So again, if you have a list of associations, you might be able to read it, but if the data gets a bit more complicated, it gets very difficult to kind of scan that structure for things you're interested in. Pass the list to grid, and you get a much nicer kind of a tabular view of um, your data. One Another cool thing about grid is you can convert a grid to a text form or text. Text is a very common markup language that's used by a lot of scientific journals, especially for things like mathematical typesetting and things like that. Um, and so it's very used in scientific journals, and researchers, people who write scientific papers, like to use Mathematica, so you can see how that might be useful to them. We're not really going to be doing anything with LaTeX here, or LaTeX, I think is pronounced, but still a nice thing to mention about grid. Okay, so let's load up another slice of our data here. So we are going to load up the top 50 names for every year, starting from just taking the whole data, um, and we're going to get a random sample of 3 years here. So in this case, it's easier to just look at the data to see what we are dealing with. So, for example, for the year 1984, the name Michael was given to 68,182 people, making the top ranked name for that year. Um, so we are looking at the short form of our data here. So each year is going to have 50 associations like that. Since we're looking at the short form, we're skipping over 48 of them, and we can just see the last one. Kimberly was given to 14,452 people, making it the rank 50th name for the year 1984. And the same thing for 2005, obviously, with different names and different counts, and so on. So this is the data we're dealing with. And this is one example where this slicing was already done for us by the initialization cells. So if you're wondering where this genderless top 50 per year variable comes from, look at the end of the notebook and you'll find how that slicing is done from the main dataset. But for our intents and purposes, we already have it done, so we'll just use it. So again, we have a little helper function here called make list, again defined at the end of the notebook, which will take a name and it will tell us where it was ranked for each year in the dataset. So here we're passing in the name Mary, and we can see that the name Mary was ranked number one in 1910, 1911, 1912, and so on. And then for the last few years, it's missing, most likely because it's not in the top 50. Or actually, probably missing data because Mary seems like a very popular name. I don't believe it won't be in the top 50. But I'll need to inspect that, to be honest. Seems a bit suspicious, but we do have the ranks for most years, so let's just proceed with this. So we are going to be using this make list function to actually start plotting producing some visualizations for two names. We're going to take Mary and we're going to take John, and um, the ranks for both of those names we are going to plot in um, four different ways. They're kind of similar, so let's actually go through each one of them just to see what is happening here. So we see two colors. The blue one is John, orange one is Mary. So on the x-axis, we have the year. So for example, 920, 1920, 1940, so on. And on the y-axis, we have the rank. Where was that name ranked for that year? So for example, we can see that for 1920, if we hover over one of the points on the plot, for 1920, John was ranked number one. So it was the most popular name in the whole of US for that year. And you can see that as the period, uh, as we get later in time, the names become less popular. Both John and Mary become less popular relative to the other names in the dataset. So in the early 1900s, John and Mary were basically always number one and number two. As you get to the especially after the 1960s, you get this sharp drop in the rank. So where in 1975, the name John was ranked 50th most popular name. So actually, that might be right. So if John is ranked 50 in 1975, that explains the missing data for the period after 1975, because it was not in the top 50 anymore. So a very simple list plot, taking two variables and just plotting them on an x-axis and y-axis, and immediately you can see how that is more useful than just scanning this list. Even if it's not shortened, you can see that you kind of get the idea. Obviously, you see a lot of ones here in the beginning, and then numbers get higher and then they get missing. But it's much nicer to visualize that on a list plot. So this is what the list plot is, probably the most simple way you can visualize data. Then we have list log plot, which is pretty much the same as list plot, except the y-axis is on a logarithmic scale. And that is useful if you have data that is very highly skewed, so you can kind of normalize that a little bit. It's very situational, but the basic idea, the fundamental idea behind list log plot is exactly the same as list plot. You just get the y-axis being on a logarithmic plot. Then the other two, list line plot, um, again, uh, exactly the same as list plot actually, but just instead of having separate dots, they are connected by a line. List step plot, again, instead of having this smooth line, you have this stepwise transition between the different data points. So we were talking about list plots. So let's move on to date list plot. And as you can imagine, the idea is pretty much the same as list plot, except that instead of having numeric values, we can have actual dates. So again, we're taking a slice of the data, which includes all name used by gender and year. Um, so we have these associations which with keys and values, and the keys are actual date objects now. So they are not kind of a simple numeric value; they are actual date objects. And if you've used Wolfram language, you've probably come across um, these object types. They're very useful because you can do all sorts of different computation with them. If you have if you have a data set with date objects, you can do, yeah, as I mentioned, a lot of computation on them. You can easily add and subtract different you can add months to them, you can add years, you can convert them to different calendars and so on. So date type objects, um, basically the same as the list line plot, but in this case we'll be using date objects. So instead of using list plot, we use date list plot. Instead of using list log plot, we use date list log plot, and so on. So nothing too interesting here. I think the main point of this, the main point of this is to show you that there are specific functions when you're dealing with date objects. Um, so this data is showing again how many males and females were in each year. So you can see kind of how the relationship between males and females counts evolved over the years. Uh, I don't think there's anything too interesting there. Obviously, they're mostly very similar, or mostly 50-50 over the years. Okay, timeline plot. Timeline plot is actually quite a nice function. So let's see what we are dealing with here. We're dealing with another slice of the data which shows for each year which was the number one ranked name in the US. And by passing that to timeline plot, we can visualize this in a very nice way. So here we have, for example, let's look at the bottom row. We have Mary, which was ranked number one from 1910 to 1930. Then in 1931, it lost the number one spot to Robert, only briefly before recovering again. Then Robert took over again, and then different names kind of had their share of time in the number one spot. It seems that the name Michael, for example, had a very long spell of being the number one ranked name between 1961 and 1998. So again, with date objects, you can pass them to timeline plot, and if it's appropriate for your data, you can get these nice visualizations. Um, okay, let's keep going ahead with more data slices and more different visualizations for those data slices. Um, so here we are loading the data that includes all name used by gender over all time. So in this case, we're not interested in the years. We just want to ask how many people were given the name Sterling uh, across the whole period. So from 1910 to 2025. And in this case, it's 6 people: Michelangelo, 489, Nicole, so on. So some names are obviously given to both males and females. So um, we can get a sample of that as well to see what that looks like. So, for example, the name Shayla was given to 27,000 people, 27,000 females, and 6 males, and so on with the other names. Okay, so let's actually start. Um, let's actually start visualizing that. Um, So you're seeing, so the data is sliced in a bit of a weird way here. So let me try to explain this, and hopefully the visualization will make it a bit clearer as well. But what we're looking at here is the top 20 names for males and females. So these little slices that you see on the pie essentially are the top 20 names. Everything else, so every name from 21 to basically all the other names, are grouped into this category called other. It's not exactly how I would slice the data if I was dealing with it, but this is what we have. Um, so essentially, we're dealing with proportions. We want to see um, what proportion of the whole data set is the name James. And if you see it's a bit small. I'm not sure if you can see on your screen, but this data slice here represents the Jameses in the data set, and you have a kind of a feeling of what percentage of all names were James. Same with John, and same with the top 20 names, um, top 20 male names, sorry, for the whole data set. And here on the right, you can you basically see the same thing for female names. So the top one is Mary, and then the other ones get a bit smaller as they go up to 20. And then this big chunk again is other, which groups basically all the names that are not in the top 20. So kind of cool. One thing you can see from the pie charts actually is that there seems to be much more variation in the female names. So the top 20 names, the top 20 female names account for a smaller portion of the pie than do the top 20 male names, which suggests to us that there is more variation in the female names, especially if and Mary is a bit of an outlier because if we look at the slice for Mary, it's pretty much the same as the slice for James and John, meaning that they're very popular names for their respective genders. Um, but with the male names, you can see that there are a lot of slices with kind of a similar size, whereas with the female names, Mary really is kind of an outlier in that sense. Um, the second most popular name is actually Patricia, but you can see that the slices get a lot smaller, and the proportion that the top 20 names take is also a lot smaller. So there we go. Pie charts very useful for kind of proportions. I see Chase has asked a few questions in the chat. With the new tabular, do you have advice on how we should pass structures like that into the visualization pipeline? When should I apply normal to association versus values? Very good question. So we do have a section on tabular, I believe. Let me have a quick scan. Yeah, we do have a section on tabular. So I'll get to that when we reach the section. But thank you for the question. Um, It's a different pie chart. Oh yeah, so they're different. So we were dealing with kind of the most basic pie chart here, but there are different ways you can kind of visualize the pie chart. You can have um, multiple pie charts nested into one another. You can have pie chart 3D and so on. But they basically, as a visualization tool, they're basically showing you the same thing. It's just a matter of styling things differently. All right. Yeah, so the 3D, we're going to see a lot of 3D versions of these common visualization options. Um, they're not doing anything too interesting, but they are immediately kind of dynamic in the sense that the user can drag their mouse and they can rotate them and so on. Counting by category bar chart. So yeah, bar chart again, one of the most kind of common visualization options. We all know what a bar chart is. We're all used to kind of reading it. In this case, we're using the males, the top 20 male names from the previous examples from the pie charts, and we are visualizing the same data um, in a bar chart. So here we have them in descending order, obviously from left to right, and on the y-axis we have the counts. But we can basically see the same thing that we did in the pie charts, in that James is the most popular name across the whole data set for males, then John, Robert, Michael, William, so on. So actually, this would be interesting to compare to the female name. So let me just do that very quickly. Females 20, because I'm curious if we'll be able to see the what I was mentioning with the female names more clearly in the bar charts. And I think indeed you can see. Um, so we're looking at the same thing for females, and you can see that Mary is very much an outlier, and that is much more obvious in the bar chart than it was in the pie chart. Um, so yeah, and on the right is just the 3D version of the bar chart. Uh, if you want to have this 3D kind of interactive effect, I think as far as the 3D plots go, the bar chart is probably the least nice. I mean, it looks a bit. I don't know. I personally don't like it. It might be personal preference, but it is there if you find a use case for it. It works just in the same way as bar chart. You just add 3D to the function name, then everything else is the same, so you can use it very easily. Um, Paired bar chart, they're actually quite useful, especially when you have data where you have two main categories. As we do here, we have names for males, we have names for females. So instead of producing, so what I did actually above, because I didn't quite know that we were coming to the pair bar chart, which is a better visualization. But what I did here is I was looking at the male ones, and I really wanted to see the female ones as well. So I just created new bar charts for that. But a much more elegant way of presenting that information is a paired bar chart, where on the one side of the bar chart you have one category. So um, in this example, on the left you have the male names, and on the right you have the other category, in this case the female names. And again, I think the main thing to see here is the name Mary in the female category being a surprising outlier. Well, not very surprising. We all know that Mary is a very common name. Chase has a few more questions. A typical example is sparkling graphics to place individual plots using around for data points against the mean of the set of data. Um, I think if you're talking about placing things in plots, I think we'll get to that in the second and third notebooks, I believe. So hold that thought, and if your question is not answered by them, feel free to kind of ping me again, and I'll get to it. Um, all right. So histograms, again, very common visualization type. And here we're dealing with a different slice of the data which just contains a list of all the names. Um, so actually, I just want to see, out of curiosity, how many names we have. We have 30,274 different names in the data set. So what we are going to do is we're going to get the letter counts of each name. Um, so for example, name Aben is 5 letters, and so on. James will be 5 letters, John will be 4 letters, and so on. And we want to see, we are going to plot these counts on a histogram, because we want to see which letter count is the most common. So to put that in a more kind of understandable way, um, how many letters is the most common length for a name in the US between 1910 and 2025. And a histogram is a perfect tool to see that. And we can see, well, we can see a few things actually. Um, Number one, we can see that the data, the letter counts follow a normal distribution, roughly speaking. Not a perfect normal distribution, but roughly speaking, they are. And obviously, the second thing we can see is that the most common letter count for names in the dataset is 6. So there are the most names with 6 letters in them in the dataset. But yeah, histogram, a very common visualization tool. You just pass it a list of some values, and it will plot those values. Um, it will plot those values on a nice histogram. On the y-axis, we see actually how many names have that letter count. So there 8,000. There are over 8,000 names with a letter count of 6, which is quite interesting. I would say if we combine 5, 6, and 7, we definitely get more than half of the actual data set. Way more than half, just by eyeball. This is not not how you do scientific analysis, but as I look at this data, I get curious myself, and I try to kind of get insights out of it. Okay, paired histogram, again, very similar idea to the paired bar chart. Again, instead of having just one histogram, you have two. Um, oh, and here we're comparing all names. I should have mentioned that we're comparing the letter count of all names against the letter count of the 50 most popular names. So we can see that even if we just take the 50 most popular names, even if we slice the data that way, we still have 6 as being the most common number of count. Um, Date histogram, same idea as um, the normal histogram, but in this case we are using date objects as the frequency data. Okay, let's see what slice of data we are dealing with here. This function gives the year a particular person with the given name was born. Okay, so this is just you pass it a name and it creates a date range. It creates a list of date objects representing when that name was given. So again, we're dealing with a simple list of values. In this case, the values are date objects, which means that we can pass them directly to date histogram, and it's going to visualize those date objects in a histogram. So we don't need to worry about conversion of date objects to any other types, and so on. But fundamentally, the same idea as a normal histogram. Here it's just a different styling um, of the histogram. Um, Instead of having this kind of bar chart looking histogram, you can have a smooth histogram, which is this smooth line that goes over. And basically, this just tells us for whichever name um, we pass to create dates. It just tells us how the popularity of that name evolved over the years. So here we're dealing with the name Abby, and we can see that Abby was really peaked in popularity around 2003, where it represented 0.03% of the of the total names in the US, which is not that a lot, but obviously there are a lot of different names. So this is quite good. Um, String data. So word cloud is actually quite a cool little function. Um, you probably have seen it with. Oh, it's very applicable to all sorts of different situations where you have um, string data. And the idea behind a word cloud is that you get a representation of all the words that are in your data set. So in this case, we have all the names, obviously, and the size of each word corresponds to the weight that that word has in the data set. In this case, meaning the names that have bigger text size are the names that are more common in the data set. So we can see that Robert, James, Michael are the first thing that we see because they're so big. But then something like Janet has a much smaller text size, meaning it's less popular in the data set. Um, Geographic data. This is quite cool. Since in our data set we are dealing with different U.S. states, and as I mentioned, the data in the data repository is normalized. So instead of just saying Alabama, we are representing that with an entity object, which means that, so as far as our data set is concerned, we only want to know that how many people with a specific name were born in that state. But since we're representing it with an entity object, Wolfram Language knows a lot more things about this entity object other than the names associated with it for current year. And one of the things that the Wolfram Language knows about all of those geographical entity objects is their location on the map. So we can kind of leverage that, and uh, we can pass geodata directly to GeoBubble chart and GeoRegion value plot, which again shows us the frequency in different ways. It shows us the frequency of the names in the different states. So again, we're taking one name just to use as an example. Here we're taking Mary, and we are seeing how many Marys there are in the different states. Um, Oh, I would like to interpret the data for you, but my US geography is not excellent. But I think um, the name Mary is very popular in California, which I believe is here on the West Coast. And you see the kind of the darker orange color, indicating that there are more Marys there, if you look at the legend. And it's there are a lot fewer Marys in the neighboring state of California, which I'm not sure which one that is, but they have fewer Marys in there. So again, kind of a nice way to visualize if your data has any geographic properties to it. Um, you should most definitely use entities for those geographic objects because then it's very easy to plot them on the map. And the bubble chart does the same thing as the georegion value plot, but instead of these outlines with different colors, you have different size of bubbles, where a bigger bubble represents higher count of that name. So we can see again in California, the bubble size is much bigger than its neighboring state. Um, but yeah, that's some basic geodata, geocomputation visualization. Okay, so let's get to tabular, which is probably the last thing we will look at in this notebook because we are rapidly progressing in time and not in content. So I'll try to pick up the pace a little bit. Tabular, as someone was mentioning, Chase, I believe, was mentioning in the chat, in the questions, tabular is meant to almost replace datasets. So we started by talking about the dataset kind of data format, data type. Tabular came along much more recently. I believe it was introduced in 14.1, I want to say. So if you're using a newer version, you have access to tabular. So what does tabular do? Well, tabular is a data type that can hold, well, as you can imagine, tabular data. But it's meant to be an upgrade on dataset in several different ways. Um, Most noticeably, it is much quicker than dataset, especially if you have huge datasets, and we're talking about datasets with millions of rows and hundreds and thousands of variables. In those cases, you will find that tabular is blazing fast compared to dataset when you do operations on it. That's the main idea behind tabular. So let's just grab some tabular data just to see how we can visualize it. Um, Obviously, tabular is very nice in the advantages that it brings, but obviously the disadvantage is that sometimes it comes with a different syntax. Um, so let's grab some data and convert it to tabular to see how we can kind of operate on it to visualize that data. So we are getting the Titanic dataset, which shows for each passenger on the Titanic which class they were in, what was their age, sex, and whether they survived or not. Um, Very popular data set for, especially for machine learning, where people train their models and so on. But in this case, the important thing is that the data comes in a dataset format, which is very easy to convert to tabular by using the function toTabular. So all we need to do is wrap our data in this toTabular function, and we have our tabular dataset, which contains just over 1,000 rows. Um, so to finally answer Chase's question is most visualization functions already know about tabular, and they can be used directly on tabular without having to convert it either to its normalized form or to a dataset. So for example, we can plot a histogram of the age of the passengers on the Titanic, and we use the Titanic tabular dataset directly. We don't have to do any conversions. We just specify which column do we want to use for the histogram. In this case, it's age, and uh, we get the histogram. Again, similar things with paired histogram, and the nice thing about tabular is we can use select directly, as you would expect. So there's nothing. It's a very easy way to slice the data at the same time as visualizing it, and it makes for some very readable code. So here we're doing a paired histogram where we're pairing. We are selecting from the data set those who have survived, and those. So we're looking at the age of those that survived and the age of those that didn't survive, and we are essentially doing two histograms paired together um, on that. Just looking at the data, nothing really that interesting between the two groups, to be honest. So, um, yeah. Um, so Chase is saying, please consider a course on tabular alone. It is fantastic, but it does have some challenges, mostly in the formatting of data in columns. I'm not sure how to control that aspect as of yet. Um, yeah, tabular is fantastic, but I have to say it comes. You're right. It comes with a fairly steep learning curve. And as for having a course on tabular, I believe that exists. So have a quick search on WolframU. I believe there were introductory courses when tabular was launched. And what was really cool about them is that they were by the actual developers of tabular, so by the people who worked at developing that functionality. So I hope they weren't just temporary videos. I hope they're kind of stored on WolframU or on YouTube or somewhere. So do have a search for that, Chase. And if you couldn't find them, just leave a message after the webinar, and I'll try to dig those out for you because they are very useful. They were my introduction to tabular as well. Thank you for the question. So just a few more things about tabular, but I'm afraid I'm not going to have time to go into this long example. The example is just about importing a CSV file, converting it to tabular, and then working with the tabular object. If you're interested in that, in what a workflow might look like, feel free to look at this example by yourself. But I think I'm going to skip to the end of the notebook because I'm quite eager to get to the other ones as well. Um, but just to summarize, this is throughout this webinar in the different notebooks, there are these elements that are very useful. In the first notebook, it's this kind of interactive table or tab view that you see here, and it basically tells you, depending on your data, um, what is the most appropriate visualization option um, for that type of data. So if your data is one dimensional, you can look at this tab and you can see all the different visualization options for one dimensional data. You can see the description of them, and you can see what the data should look like, and you can very quickly decide. So what I would advise you to do is save this table from the first notebook, save it in a document somewhere, basically for safekeeping. And if you're ever in a position where you need to decide what visualization to use, just put that up, and I think it might help you a lot. I especially like this when you hover over the functions, you can see an example of what that visualization looks like. Uh, that, alongside with the descriptions, makes this a very useful table. And we have the same for 2D data, all sorts of different visualizations, for 3D, 4D, matrices, graphs, financial. So probably the last thing I want to mention before I move on to the other notebooks is that we have a lot of in Wolfram language. There are a lot of visualizations built in for different areas. Um, and in this case, we're seeing for finance, we have candlestick charts, trading charts, Kagi charts. So these are charts that are typically used in finance and pretty much nowhere else. And so if you are in some kind of specialist area where you might be looking, so for example, if you are in finance, you might look at the basic visualizations and say, well, that's not what I need. Actually, I want to display a Kagi chart to my colleagues. um, so even if you are in a specialized area and you need a very specific type of chart that you kind of assume wouldn't be built into the Wolfram language, have a look. The chances are it might be. I'm not saying that the Wolfram language has every single possible visualization in the world, but it's always worth checking. So these are the ones for finance, but there are others that are not listed, and which we should probably expand this tab view since it's so useful. But for example, for biology, there I think it's molecule plot 3D. Let's see if we can plot some molecule. Caffeine molecule. I'm not sure if this will work, but and it did. So yeah, a lot of specialist areas have a lot of their own specialist visualizations. So the best thing to do is to just go to the documentation and search for whatever you're interested in. It might be there, it might not be, but it's always worth checking. All right, so that does it for the first notebook. uh, i'll I'll glance over some of the next ones, and I'll move to the last one so we can build our own kind of custom graph. Okay. Chase is saying thank you for the suggestion. He found the tabular tutorial, I believe. Yep, absolutely. That I believe that is it. Let me just. Yeah, that is it. So I'll publish that. I'm glad you found it. I'll publish that. So if anyone else is um, interested in tabular, it's a very good. It's a series of videos where the developers, each developer talks about their kind of own specialty and kind of the overarching um, idea of tabular itself. So yeah, very useful. Um, yeah, I'm glad you found it. All right, so we are going to notebook number 2, themes and styles. So these notebooks are quite long as well, so there's no way I'll have the time to go through all of them. So I'll just um, try to leave you with the most useful things out of these notebooks, and then if you're interested um, in more detail in any of these, feel free to look at them yourself. And if you are interested in kind of going into more detail in data visualization, as I mentioned, these materials are from a WolframU course that is much longer than an hour and a half. So if this looks interesting and you want to spend a few more hours on that, feel free to check out that WolframU course as well. But the main thing, so as I was mentioning in the first notebook, the main useful thing that you can basically copy and paste and keep for your own reference for a later point in time was that tab view with the different visualization options. So these notebooks, so notebook 2, 3, and 4, have a lot of these interactive elements where you can manipulate different aspects of the plot with these nice dynamic menus, and you can see immediately how it reflects on the chart itself. And the cool things about these interactive menus is you can experiment very quickly with different visualization options without having to write the code. So you have these drop down menus where you can change the theme and so on. And once you're happy with something, you can copy the actual code that is used to produce that visualization. So let's say I'm happy that I need to use a line chart, a list line plot, and I want to quickly experiment with different visualization types. Um, and let's say I'm happy with this one, I can just say copy to clipboard, and I can paste this somewhere else, and this should this should work. Why is it so small? Oh, because it's thumbnail. Anyway, you get the idea. It makes it very easy to experiment with different element types without going back and forth between the documentation, writing the code, saying, "Oh, that's not what I want. Let me try a different option." Instead of that, you have this really nice drop-down menu way of doing things. And in this notebook number 2, there are these dynamic elements for list line plots, pie charts. Again, you can experiment with those. Color choosers. I think the most interesting one in this case is the blend example. So just spend a minute maybe on blend. Um, so in Wolfram language, you can specify basic colors. So symbols like blue actually refer to a color. So whenever you need to color something, you can just pass the word blue, and Wolfram language understands that you're referring to the color blue. Um, You can also obviously create your own colors using RGB values, hex values, and things like that. But one of the cool things you can do is you can create blended colors or gradients using, I believe it is blend. Um, and then you can use that blending of colors to color a plot. For example, this 3D plot here is colored using a blending function. But how do you actually create a blend? Well, you can specify a blend between different colors, and that's absolutely fine. So we can have blend blue, red, and so on. But this dynamic menu that you see here is especially useful for creating blends. So instead of saying blend blue red, I can say that okay, the first color should be red, the second color should be green, and so on. And obviously, once you have created a blend that you're happy with, you can again copy it to the clipboard, and you get the code that's used to produce that blend. Again, very useful stuff. Um, Point size, again, this is about manipulating different elements on charts. So all of these, again, what I would do is just keep the whole folder with these materials somewhere. Believe me, when you're working with your own visualizations, this will come in handy. Uh, uh, it will make it much easier to experiment um, with graphics. So this was it for the second notebook. Obviously, I'm skipping over a lot of things. Notebook number 3 is very similar in spirit to notebook number 2, but instead of manipulating different elements of the chart itself, it's all about labeling. So again, you in Wolfram language, the labels can be placed basically on an arbitrary point on your graph. Obviously, there are some predefined ones, like the title of your chart goes above the chart and so on. But really, you can place labels anywhere on the graph. And these dynamic menus here, let's just try this. These dynamic menus let you experiment with placing your labels uh, in different positions, and also with frames and things like that. Again, probably the easiest way to experiment with those things rather than um, rather than looking at the documentation and writing the code yourself. So again, not going to go through all of them. There are these menus for all sorts of different line plots, pie charts, sorry, not pie charts, 3D graphics. Yeah. So callouts. I mean, you can see even for a simple thing as a callout, and by callout we mean whenever you have a data, you have this callout label that specifies what the data is. You can see how many different options you can specify for the callouts. So obviously, all of these are excellently documented on the documentation page. Um, but instead of kind of experimenting with all those different options, you can do it. Um, you can do it with these simple menus, which makes it much easier. Once you're happy with something, copy the code, use it in your own visualization, and so on. All right. So yeah, same idea for all of these. Arranging element. I'm not even going to go into this notebook because it is exactly the same idea as the previous two. I'll just say that somebody asked the question: is it possible to have two plots of the same object next to each other, but with a slightly different viewing angle in one direction for stereoscopic view, and then rotate both simultaneously with the cursor such that they all the time keep the same difference in viewing projection angle? Okay, so I think you will. So you want, for example, if I go back to the first notebook, let's say where I created the bar charts. Oh, I didn't save them. So let's say you have two bar charts together. You want them, or let's say two 3D bar charts together. You want them side by side from a different angle, and when you rotate the one, the other should rotate as well to keep the same viewing angle. I would say that's definitely possible. You would need to just trying to think of the best way to do it. First, look into graphics row, which will let you have both of them together. I think the most challenging part of your question is when you rotate the one, the other should rotate as well. So what I would do to achieve that is I would wrap them in manipulate, and um, I will have one variable that stores the viewing angle, and then I'll pass that variable to both of them, which should ensure that when you rotate one, then the other should rotate as well. But this is just off the top of my head. So have a look at graphics row, have a look at manipulate, maybe have a module inside where viewing angle would be one of the variables, and then pass this viewing angle variable to both of them. Um, yeah, that's how I would approach it. Um, so hopefully that helps. Have a go yourself. If you're not able to achieve it, drop us an email, and I'll see how I can help. That's a cool use case. Oh, you were thinking of 3D figures like the 3D molecule view. Yeah. The same principles should apply whether we're talking about bar charts or 3D molecule views. Um, I'll try out your suggestion. I use manipulate but had difficulties. Yeah, manipulate is another extremely powerful function, but with a slightly steep learning curve. Um, yeah, have a go. I think it's definitely possible with manipulate, but have a go yourself and see how you get on. Jay saying WolframU is terrific. I need to set up a reoccurring task to see what's new there every couple of months, like a tablet. Yeah, WolframU is terrific. Our colleagues over in America do an extremely good job. They have, I mean, we do these live webinars, which I think are really cool because we get all of this engagement with you guys. But typically, our webinars are just about hour and a half. The guys at WolframU do 2 hours, 3 hours, 4 hours sessions. So really, really excellent stuff. So yeah, have a look at that as well. So let's get into the last notebook, which will occupy the next probably 10, 15 minutes. So so far we have been looking at just basic, out of the box, ready to go visualizations. But one of the very powerful things you can do with Wolfram Language is you can take graphical primitives such as axes and labels and callouts and menus, and you can combine them. You can combine them together in your own kind of custom graphic. So what we are looking here in the last notebook is three examples of creating custom graphics. So the first one is the bubble chart and the bar chart. The second one is this kind of blended bars with ears on the x-axis, and the third one is the line chart. So what we're going to focus on is the second one, a visual history of U.S. baby names, which is a really, so as you can see immediately, this is not an off-the-shelf graphic. There's no function built into the Wolfram language that produces exactly this. So the idea is we have this vision of what the graphic should look in our head. So let's actually build it. And just to tell you what's happening here, so let's actually look at the graphic because it's not. I mean, it's very useful, but it's not immediately obvious what is happening. So let's just spend a minute just talking about what the actual end result will be showing. So we have a list of names. So we're looking on the left. We have a list of names, and one of the things we'll be able to do is we'll be able, with this menu on the top right, we'll be able to add more names to that list. But we have a list of names on the x-axis. We have the years, which is fairly obvious, and um, then the actual color of the bars is the legend for that is on the top left. So we'll be looking at the rank of each name, where we have this blended um, color gradient, where a dark purple will mean a higher rank, with the darkest purple being rank number one. So we can see, for example, in Michael, he was well, he the name Michael was ranked number one in this very big period between the 1970s and the 1990s. And then the lighter the color goes, that means that the rank goes up. So Michael was not that popular in 1940, for example. In addition to all of that, we have here on the right hand side, we have years in the top two, which is a simple numeric value. How many years was this name in the top two names in the country? So again, going with the Michael example, not only do we see how the popularity of the name Michael progressed over the years, we can see how many years exactly the name Michael was in the top two names, and the answer is 54. The name Isabella was in the top two for 2 years, looking like late 2000s maybe. So this is the idea of a graphic. It's quite a nice looking graphic. I think it puts a lot of things together, and it's still understandable, even if it's not immediately obvious. So cool. Let's see how we can build that. I'll scroll past the bubble chart, even though that's quite nice as well. Okay, so the graphic we are interested in starts from this section, more baby names. Um, let's load everything. So we start with the data that we started at the beginning of the webinar, just the different baby names in the US for that period. The first thing we are going to do, and here is a bit of a data cleaning and data slicing, we are going to get the top two names for every year. I'm not going to go into the data slicing code because that's less interesting. Let's actually move on to the visualization. So here, basically, we are just preparing the data that we're going to plug into um, our graphics. All right. So okay. So here we are starting to kind of build our graphical primitives. So the first thing we're going to do is we are going to define a blending function. Um, And here again, if I was doing this from scratch, what I would do is I would go back to one of the other notebooks. where that blending dynamic element was in, and I'll just do that there instead of specifying the colors myself. But here they are already done for us. So we're saying for the value of 0, the color should be dark purple. Obviously, the values it goes from 0 to 1. So we're saying at this extreme, the value should be purple. At the other extreme, the value should be this light yellow. And then it should pass through kind of a light purple and orange-ish. All right. So we can test that our blend works as expected by taking one name. In this case, we are dealing with, what are we doing? We're dealing with Mary. And so what we expect is if the name is rank number 1, it's going to be dark purple. The higher it moves up the ranks, it will be colored with this light yellow. So perfect, that works. We are defining a few other kind of helper functions to get this nice bar at the end. Um, and we are also going to do some font styling for the actual names, how they will appear on the graph. So obviously, if we don't specify any font styling, Wolfram Language is just going to use the default font for your machine. But in this case, let's say we want to say the color of the font should be gray, the font itself should be this one, and it should be bolded. So if you look back at the final product, this is the names you see here on the left. So this styling kind of makes them fit in a bit more nicely with the overall graph. All right, so let's keep building our graphical primitives. So far we've got the bars, which are really underpinned by this blending function. Um, and we also have the names, which are styled with a different color and with a different font. So now that we have the names, we can arrange them in a grid. So this is the big chunk of our visualization. So we already have the blending functions. We have the names. We have the styling for the names. So all we do now is we put them in a grid. And as you can see, that already gives us most of our graphics. And you can see each element is its own thing. So it's not uh, just one image where you can do anything. You can interact with this. You can click it. Oh, in the case of colors, I don't think you can do much with the colors, but you can change things like the numbers here and so on. Okay, so the next thing we are going to do is we don't have any axes, so we're going to build just a simple axis. We are going to build our x-axis, which goes from 1910 to all the way to the end of the range, which is 2014 is actually when that data ends. Next, we're going to build our legends so that people who are looking at our final graph have an idea of what they are looking at. So we use the same blend, and we add a bit of descriptive, like the title and the rank number and the colors. All of that we already have. We're just putting it in a nice kind of element of its own. Then what we are doing is we are putting all of these things together. So we had the graph already. Um, we are putting the axis that we created at the bottom of the graph, and we are putting the legend that we built on top of the graph, top left. And there's many different ways we can play with the positioning of these elements, with the styling. So yeah, you can look into those yourself. Um, then the next thing we're going to do is we're going to add, I believe, the interactive menu. Yeah. So again, we are taking a name list, which this name list again will probably be populated in the initialization cells, but we have a list of names and we want to create this panel where users can select the name. So this is what that looks like. So you have a list, a scrolling list of all the different names, and you can click on them. And then we use that menu again. Here the code gets a bit more complicated, but there's nothing super complicated. It's just it will take a long time to explain it, but I can tell you what the end goal is. And the end goal is you have this menu with all the different names. When the user clicks on them, the top row is replaced by whichever name they clicked on. So you have the most or some of the most common names in the graph by default. But if the user is interested in some other name, they can find it in the menu and click on it and immediately see the data for that name. So let's say we're interested in Jack, which would be quite not as popular as I would have assumed. But there you go. This is the whole example. Again, glossing over much of the code. But I think that what's important in this example is the idea that you can build separate graphical primitives and in even things like interactive menus and so on, and you can bring them together in one final graph. So even though there are a lot of different visualization options in Wolfram language, you're not really restricted to any of them. You have all the tools to kind of build graphical primitives and put them together. So if I was working with this chart, for example, I would, instead of having this menu, which is really nice, where users can click, I would probably let them have a text box or an input field where people can type the name they're interested in. And if it exists in the dataset, it would get appended here as the top row. But there are many ways you can take that. And again, this is one of the nice things in Wolfram languages. Everything is kind of designed to work seamlessly together. Um, so if you're plotting, if you wanted to create that graph in, let's say, some other programming language, or maybe you can create the graph itself, but then when you get to this interactive menu, you would either have to code it from scratch, rely on some external library that works in a different way, and so on. Whereas in Wolfram language, you have everything together in one place. It makes building things much quicker, much more reliable, and much easier. I'll just show you one of the other kind of custom graphs because this is quite cool as well. But that will probably be the last thing we can get to in this webinar. So I'll just evaluate all of the code here just so we can get to the final product, and then we'll see what that looks like. The idea is the same, by the way. We're building separate elements and we're putting them together. We're obviously adjusting things like labels and styling and so on. So actually, this code might take a little bit because it's doing a lot of I think it's looking up a lot of properties of entities at some point in the code, if I remember. But let's just give it a minute to evaluate all of that. And we'll talk about what the final chart means. I'll tell you what. Let's just leave it to evaluate, and I'll look at the actual screenshot of the final chart and see if we actually get it in the notebook. It should work in the notebook, so I'll keep an eye on the code evaluation just to see if there's an error somewhere, but it should work. I tested all of them before the webinar, but let's just look at. So this is what the final result will look like if our code works. So here we have a bubble chart on the top, which compares three different factors, three different variables. You have literacy rate, which is on the x-axis. You have life expectancy in years, which is on the y-axis, and you have population, which is represented in the size of the bubbles. So the bigger bubbles represent countries with higher population, and then you also have different coloring for the continent that the country belongs in. Oh, I think the code has finished evaluating. So let's see if we can get the actual live version of this, because it is quite nice. Yeah, we do have it. Perfect. Okay, this is this is much better. Okay, so as I was mentioning, literacy rate, life expectancy, population. So you see, if I hover, for example, over this big yellow bubble, I can see that it's India. Obviously, India has a very large population, so that's why the bubble is so big. And then um, a fourth element that we're looking at is the continent that the country belongs in. So we have this color coding scheme um, here on the right. And you can see that even with a 2D graph, you can represent four different factors. Again, it tries to bring a lot of things together in a single graph, and all of those things are built individually and then just put together. So you can see when I hover over something, I have a nice tooltip on the top left. Again, this is one of the things that we build while we're doing the graph, and then we just integrate it as something that appears on hover. So if you're interested in doing things like that, have a look at kind of the source code for this, and that will get you started. Um, yeah, I think this is all we have time for. Um, as I mentioned, with so many functions in the language, it's kind of difficult to get through all of them, especially in an hour and a half. But I think we have covered all the basics. So we have covered the most common visualization functions, your histograms, your bar charts, line plots, and so on. We have covered some of the useful dynamic menus that exist in those notebooks that you can definitely use yourself at a later point. And we have also covered the main idea that you're not restricted to all of those pre-existing charts. You can use graphical primitives to build your own, and not just graphical primitives, but anything in the Wolfram language, like interactive menus, like input fields, like tooltips, and so on. So apologies that I couldn't get through all of the material. If you're interested, um, either have a look at the notebooks for yourself, or check out the WolframU course, which I believe is 3 hours and a half, which will go through the same material but just in much more detail. Um, so thank you for attending. I wanted to see if anyone has any questions. Ray is asking, is it possible to force the labeling a point in a list plot interactively? Does the plot have to be generated for each time label? Um, which let me try to read this again. Is it possible to force the labeling a point in a list plot interactively? Okay, so we're talking about list plots and we're labeling a point. Does the point have to be generated for each time label? No, you can have it either as a static label, as a callout, or you can have it generated interactively, for example, on hover and things like that. So you can do it either way, but the plot doesn't need to be generated each time for each label. Sometimes not all points have enough room for labeling. Oh, I see what you mean. So I mean, there are a few ways you can go around that. Let me see if I can quickly find one of the menus that I was talking to you about. I don't think I'll be able to. There are so many things. Oh, maybe here. Okay. So this is a bar chart, and as you can see, well, if I make it bigger, it works. But if it's the default size, you can see that there's not enough room for all of the labels. So there are a few ways to get around that. I mean, one way is to only have labels for some of them, but probably a much nicer solution is to rotate the labels at an angle, and then you can see all of them. It's still not very nice visually, but that's one way of getting around it. Another way, which I think Ray was alluding to, is to have the labels appear on hover. So typically you would have no labels, but when you hover over a bar, you can have um, the name appear. So there are different ways of doing it. Um, but yeah, definitely, yeah, whichever way you prefer, whichever way works for your use case, I would say.